I saw her walk out and, yeah. Okay. So here's the next unit. So now we've kind of gone from like linear motion with acceleration of forces into centripetal motion, and now we're going to go into momentum, which is going to combine eventually both worlds into the same idea. So momentum in and of itself is the simplest equation you will ever see. Okay? It is literally
Muy bien.
just momentum equals mass times velocity. Okay, that's it. Now, the reason, and you say, well, if it's momentum, why is it represented by the letter P and not M? Because then you'd have like M equals mv, and that would just be awkward. Okay, so that would just make things confusing, because then you don't know which M that you're solving for. The other reason that they use the letter P is because there was an old idea that they had when they were trying to figure out this concept of motion, and they called it impetus. So the idea of impetus was that when I made something move like the squirrel, okay, I would give it a certain amount of impetus. And when the impetus ran out, the object would stop, okay? So if I just give it a little bit of impetus, it would only go a little bit of distance before it stopped, okay? If I gave it more impetus, okay, and threw it faster, then it would go further before it stopped. So you can kind of view it as like a fuel tank on your car. So if you fill your tank up, you can drive a long way before you run out of gas. If you just put a little fuel in your tank, you can only drive a little bit of distance before it runs out. So that's where the letter P came from, and that was that old idea of impetus. So they said, oh, there's a P in it, let's just use that. So, in terms of units, so here's as simple as it gets. So here I've got a golf ball. Let's say that it has a mass of 0.1 kilograms. And all I have to do is multiply it by the velocity. So if the velocity of the tennis ball or the golf ball is 5 meters per second, mathematically, this is as simple as it gets. You just take 0.1 times 5, you get 0.5. Now, with the units, you have a decision to make with the units, okay? Option number one, you can go old school and just go kilograms, meters per second. Now, this is not force, okay? Because force is mass times acceleration, and that's kilograms, meters per second squared. This is just kilograms, meters per second, okay? So if you're old school, it's just kilograms, meters per second, because it's kilograms times your velocity, okay? Old school. Now, you'll see why this works later on. You can also express units of momentum as Newton seconds, okay? So the reason that this works is because newtons are kilograms, meters per second squared. And then when I multiply it by seconds, the seconds cancel out, and you're back to kilograms meters per second. So in terms of units for momentum, I don't care how you do it. You can do kilograms meters per second, you can do Newton seconds, it's whatever floats your momentum boat, okay? Just pick one. So, is it possible for momentum to be a negative value?
No.
No. Well, no.
I guess.
So, if the golf ball was going this direction with positive velocity,
But then there was momentum acting against it.
no, don't throw that into it. This direction is defined as positive. So if I make it go in the opposite direction, what has to happen to the sign of the velocity?
It has to change.
Negative.
It has to be negative. So can velocity be a negative value?
Yes.
Yeah, throw it up in the air. On the way up, what's the sign of the velocity? Positive. On the way down, what's the sign of the velocity?
Negative.
No.
So if the ball goes in the opposite direction, I would just take 0.1 kilograms times negative 5 meters per second, and I get negative 0.5 Newton seconds. So because momentum can be both positive or negative, Do you think momentum is a vector quantity or a scalar quantity?
Vector.
It's a vector quantity. So if you define one direction as being a positive value, oh, that's positive 0.5 Newton seconds. If it was going in the opposite direction, that's going to be negative 5 Newton seconds. Okay, cool. Now, because it's just mass times velocity, there's nothing squared, we're not dividing by anything, there's no inverse relationships. If I double the velocity, what's going to happen to the momentum?
Doubles.
It'll also double, okay? So if I make it go twice as fast and go 10 meters per second, hey, my momentum doubles to 1 Newton seconds, okay? Everything's just linear, there's nothing square, there's nothing wonky about it. Now, here's the next question. Do not confuse momentum with inertia, okay? They're related, but not the same thing. So, is it possible for Hank and the golf ball to ever have the same inertia?
Yes.
No.
No, because they weigh
It's
different.
just based on mass.
They have different
What's the only
masses.
thing that determines inertia?
Mass.
Mass.
Oh, mass.
That's it. Not weight,
Mass.
mass. So it's always going to take more force to get Hank to move than it is to make the golf ball move. Okay? Because Hank has a lot more stuff. Now, interesting thought. Now that we've studied astronomy and gravitational fields and all that good stuff. If I take this golf ball to the moon and make it move at 5 meters per second, how will the momentum on the moon change versus the momentum on the Earth? Caitlin?
I don't think it would.
It won't.
It won't change. Why?
Because it's mass and velocity.
Yeah, it's mass times velocity. If I'm on the moon and I make the golf ball move with a certain velocity, it's going to have the exact same momentum on the Earth as it does on the moon. Because it's just mass times velocity. It's weight times velocity. Okay, cool. Now, would it be possible, assuming that these are non-zero values, to have the bowling ball, Hank, and the golf ball have the same momentum?
Yes.
If they have different velocities.
Different velocity.
Okay, let's get a little bit more specific than different velocities.
If that weighs 10 times more but was going at 10 times the speed, it would have the same momentum.
Close. Let's swap out mass for weight.
If it had 10 times more mass, then it went 10 times.
Bingo.
That's
So if you look at momentum, so here's Gary the golf ball, and there's Hank, okay? So Gary the golf ball has a small mass. But if Gary the golf ball was moving really fast, that could have the same momentum as Hank, who has a large mass moving
With small velocity.
with a small velocity, okay? So here's the story. So objects that have different mass can never have the same inertia, because the only thing that determines inertia is mass. So two objects, different mass, can't have the same inertia. But two objects with the same, with different masses can't have the same momentum, because there's two things that affect momentum, and that's mass and velocity. Okay? Got that idea?
Yes.
Now, obviously the test, and momentum is a relatively short unit, we just do linear momentum and then we do angular momentum. So, I'm not going to give you 30 problems where I say, oh, the momentum is 20 and the mass is 1 kilogram, find the velocity, or the mass is 5 and kilograms, so it's moving 10 meters per second, calculate the momentum, okay? It's not the point of the story. The point of the story is actually if we can change the momentum. So that's the next question. Is it possible to change the momentum of an object?
Yes.
Yeah.
Yeah.
Pretty simple. We just push it. Right.
Change the velocity.
Change the velocity. So for now, we're going to assume that the mass remains constant, okay? Once we get into rocket engines, you'll see that that isn't true, okay? But for now, we're going to assume that the mass is constant. So if I drop the golf ball, what's the initial momentum of the golf ball?
0.
0.
0. Cool. As it falls, what happens to the amount of momentum?
Increases.
It increases. Okay, cool. So, to make the math easy, let's say that down is going to be a negative value. Okay? So, let's say that that's 0.1 kilograms. There's going to the golf ball, we're going to drop it. Down is being defined as a negative value. So, if I know when it lands, let's say that it's going negative 6 meters per second. Okay?
Yeah, 6 meters per second, right?
Negative.
Negative 6.
Yeah, I see. Yeah.
So it lands with a certain amount of momentum. Do I have enough information to calculate the final momentum of the ball when it hits the ground?
Yes.
C6.
Right? Because if I take 0.1 times negative 6, I get negative 0.6 Newton seconds. What was the initial momentum of the ball?
0.
0.
0. So P naught is going to be equal to 0. It doesn't have any momentum. Right as it hits the ground, it has a value of negative 6. Cool. So look at it this way. Could we look at this in terms of a momentum time graph?
Mm-hmm.
Yes.
It's a new graph, momentum time graph.
I think we could do it.
With the slope.
What's the initial momentum of the ball?
0.
0. Now, when I drop it, what's that graph going to do?
It's linear.
It's gonna it's not linear, it's gonna slope, because it's like the velocity.
I thought it'd be
How
like
does
this,
that
but
work?
going down.
Linear. And
Hold
then
on,
linear.
stop, whoa, stop. Okay. Do you agree that it's going to end up somewhere down here?
Yes.
Yep.
Okay, you know it's going to end up here at negative 0.6 Newton seconds, right? You know that's where it's going to end up. The only question is what's the path that gets it there? Okay, that's the only thing, that's the only variable that we have. So let's start with this idea. We'll just worry about units, okay? We'll worry about numbers later. What units is momentum measured in?
In seconds.
Newton seconds, okay? Time is obviously going to be in
Seconds.
seconds, right? Cool. So the slope of the line would be change in y over change in x. True?
Yes.
So that would be Newton seconds divided by seconds.
Oh, the seconds cancel.
So slope represents the force.
Ah, slope represents the force,
Whoa! Oh my goodness!
okay? Now, but this is subtle. Does the slope represent force or net force?
Oh,
Net force,
Why?
because it's the total forcing.
Well, look at it this way. If I just hold the golf ball, are forces acting on
Yes.
Yes.
the golf ball? Is the momentum changing?
No.
No, because right now, what's the net force?
0.
0. But if
oh.
I drop it, does the momentum change?
See,
Yes.
Because then,
the net-
what else is it doing besides momentum changing? It's also perhaps accelerating. Oh, cool. So, let's think this through. If I drop the ball, speaking of the acceleration test, if I just drop the ball, does it accelerate?
Yes.
Yeah.
So if it's accelerating in a linear fashion, we're done with circles for now. We'll circle back to circles. So if I just drop it,
Probably.
the velocity changes. So if the velocity is changing, what else is changing? Momentum. Ah. So if I'm going to change momentum, I have to change velocity. But to change velocity, what do you have to have?
Acceleration.
An acceleration. But to have an acceleration, you have to have a non-zero
No.
net force. Okay? So just because a force acts on an object doesn't mean the momentum is going to change. You set your cruise control at 60. Okay? Let's talk about momentum being a vector quantity. In terms of momentum, what's the function of your gas pedal?
Accelerate.
In terms of momentum,
Velocity.
Increase.
Increase.
make your momentum vectors bigger,
Yeah.
right? Okay? What's the function of your brake?
Decrease
Small.
the-
Make it smaller.
Make it smaller. What's the function of the steering wheel?
Change direction.
Change the direction of your momentum vectors. Cool. What's the purpose of cruise control?
Keep the or keep it the
To
same.
keep the same momentum vectors. Okay? So if you have cruise control on, does that mean that and you're not accelerating, does that mean there aren't forces acting on your car?
No.
No, but just all the forces add up to
0.
0. Okay. Now, let's go old school.
So it doesn't.
You know, V equals V naught plus AT. I want to know how long this ball is in the air. Okay? I want to know how long the ball is in the air. What's my initial velocity?
0.
Zero.
My final velocity is negative 6 meters per second, and that's going to equal AT. So how can I figure out how long it's in the air?
Divided by negative 9.8.
So somebody take negative 6 and divide that by negative 9.8 meters per second squared.
We need Louise.
We need Louise. He's our calculator guy.
Yeah, he usually has it out.
0.61.
He's usually prepared.
0.61?
Yeah,
Yes.
negative 6 divided by negative 9.8, right?
Yep.
Yeah, 0.61.
Okay.
On the dot?
So this is going to be 0.61 seconds.
Wait a second.
That seems-
What'd you do?
0.612.
I call it 0.61.
Analog.
Close enough. Okay? So the question is, what's the shape of that line in between? Is it a linear function or is it a curved function?
He was just like, "Oh, test."
Now, let's just back up the bus for just a second. If you want to change momentum, right?
Yeah.
That means that you have to change velocity. True?
True.
Yeah.
See?
Does velocity change as a linear function of time?
Sometimes.
Sometimes.
If the only force acting on it is gravity, how about that?
Yes.
If gravity is the only force acting on it,
Yes.
yes. If gravity is the only force acting on it, velocity changes as a linear function of time.
Yes.
So if change in momentum is a product of mass times change in velocity, because that's like one way to calculate change in momentum, is mass times change in your velocity. So think this through. If velocity changes as a linear function of time, what do you know about momentum?
Linear.
It's also going to change as a linear function of time. Cool. Okay. Now, so at this point, according to Dylan's oracle, we started at 0, 0, and we end up out here at 0.61 seconds and negative 0.6 Newton seconds, right? At this point, can we find the slope of the line?
Yes.
Yeah.
Yes. We got 0, 0, and 0.61 and negative 0.6. Okay? So at this point, we can find the slope of the line, because the slope of the line is change in y over change in x, right? So Dylan, you have your calculator out, right?
Yes.
So I need you to take negative 0.61 Newton seconds
Yep.
and then divide that by 0.6, that was 0.6 Newton seconds. You gotta get that right. 0.6 Newton seconds and divide that by 0.61 seconds. What do you get?
Negative 0.983.
Negative 0.98 newtons. Ah, that's kind of cool. It's a 0.1 kilogram
Oh,
mass.
oh my gosh.
Almost 9.8.
Times 9.8.
Oh.
Go.
Because a 0.1 kilogram mass weighs
0.98
0.98 newtons. So when I drop it, what's the only force acting on it?
gravity.
Gravity.
That becomes the slope of the line. Okay.
Mm.
Now, let's step back for a second. So here was Gary the golf ball. Gary's graph on a momentum time graph, here you are at 0.61, or 0.61 seconds. And Gary's line went like this. So Gary's here at negative 0.6 Newton seconds. So that's Gary's line. That's Gary the golf ball. What would Hank's line look like?
Steeper.
If assuming that I drop Hank from the same height.
Steeper.
It'd be the same. Just kidding. I lied. It'd be steeper.
Is the time for it to hit the same?
Yes.
Yes.
Yes,
Yeah.
because they both have the same acceleration,
Yeah.
right?
Mm-hmm.
So Hank is also going to land at 0.61 seconds.
Correct.
True?
Yes.
True. But here's the kicker. What's going to have more momentum when it hits the ground?
Hank.
Hank or Gary?
Hank.
Hank is, right? I'll put my hand out here and drop Gary and catch it. I'm not going to do that with Hank.
The
Okay.
momentum will break your hand.
The bad things are going to happen. What happened to your hand, Camp? Physics demo gone bad. Okay? Victim of momentum. So
I feel like if one's gonna go bad, it's gonna be the brick.
Hank's line is going to be out here. What does the slope of this graph give you?
Newtons.
The force.
The force. When I drop it, which has more force acting on it?
Hank.
Hank. So that line's going to be much steeper because he has a lot more force acting on it. Okay? Makes sense. All right. New graph. Force time. Okay? So when I drop Hank, let go of him, what's the only force acting on Hank?
Gravity.
Gravity. And Hank weighs, assuming that Hank has a mass of 0.1 kilograms, and I multiply that by G, I'm going to get negative 0.98 newtons. Now, according to Dillon's oracle, Hank fell 0.61 seconds, right?
Here.
Okay.
Come on.
So, when I drop Hank, does the force change as he falls?
No.
No, it stays the same, right? Because that's the only force acting on him, true? Okay. So, this is going to be a horizontal line like this. So that's negative 0.98 newtons, and this is 0.61 seconds, okay? So do you think I'm capable of finding that area?
Yep.
Yep.
Yeah.
It's a rectangle, right? So Dylan, do us a favor. Take 0.98 newtons, negative 0.98 technically, and multiply that by 0.61 seconds.
It's momentum, right?
What'd you get?
Negative 0.5978.
So negative 0.60?
Whoa.
Units of Newton seconds, right?
Wait, what is it? Negative 0.00?
So notice that matches up with the change in the momentum. So here's the big idea. So, and this is technically force net. This is net force. This is net force. It's not force, it's net force. So if you have a net force versus time graph, the area is going to represent the
Change in momentum.
change in momentum. Okay? So here's the big idea. If you have a momentum time graph, so on a momentum time graph, the slope represents force. But if you have a net force versus time graph, the area represents the change in the momentum. Okay? Now, is it possible to exert a force on an object, but yet not change the momentum?
Repeat the question?
Is it possible to exert a force on an object
Wait, yes.
I
I'm
say no, but
saying
I can
no.
change.
and
it.
not change the momentum?
Yes.
No.
No.
Yes.
Yeah.
Look at all of you. Are forces being exerted on you right now?
Yeah.
Yes.
Oh, yeah.
I said no.
I said yes.
I think
Yeah, you're
no.
wrong.
You're
I
Is
said
your
yes.
momentum changing?
No.
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 I said yes, by the way.
Force is acting on you, but your momentum isn't changing. Now, I won't do this because I like Gavin. But if I were to go up to Gavin and pull the chair out from underneath him, what would happen?
You'd fall.
I don't know, man.
He'd begin to accelerate. Why?
Force,
Did he fall?
gravity.
Because then there would be a net force acting on him. And then he would begin to accelerate. So forces by themselves don't create changes in momentum. But net forces or imbalance forces create acceleration. That creates a change in momentum because that creates a change in the velocity. So this is all about the vocabulary. Net force versus net. Okay? Or versus forces. Okay. So Dylan, come up here.
Oh, no. Oh, never mind. This might not be no. Why do you drink the orange Red Bull? I'm pretty sure that one's bugs.
That looks good.
Okay.
I don't.
Get over there.
I would know.
So here I have a raw egg.
Oh, wow.
Okay? And you can tell if a cook is raw or cooked, if you spin it
Yeah.
and stop it and it continues to spin,
Oh, the
Because
liquid
the stuff
inside.
inside it.
yeah, because the stuff inside has momentum. So, and you don't stop it and then it continues to spin. Now I'm gonna throw this to you.
Wait.
It's a raw egg, okay? I don't want it to break. So how are you gonna catch it?
1 and 3.
What are you gonna do with your hands?
Probably try to catch it.
I got that part.
Catch it, but then also like
Are you gonna move your hands in the direction that the egg is moving or in the opposite direction of the egg?
Probably with the egg.
With the egg.
Yeah.
Okay, you ready?
No.
Tell me when you're ready.
Okay.
Okay, you ready?
Yep.
Okay. Now, why did he move the egg? Why did you move your hands in the direction of the egg?
because that's where the momentum was going from trying to.
It doesn't want to break. But now your explanation, Elliot.
It's in the direction the momentum was going, so he was trying to allow it to keep going some, but also start slowing it down.
Decelerating the momentum.
No, not that one.
Throw the egg.
Okay,
Like-
throw the egg back. So,
Throw the egg at him.
instinctively, if it's something fragile, you do this. Okay, we're done, thank you. I'll need you to get it, that'll be
Has
it.
anyone ever not caught it?
Yeah.
Oh.
So, here's the egg as it flies through the air, okay? So, we just proved that force times time, which is the area under force time graph, and that's technically net force versus time, equals change in momentum, right? Now, since the beginning of this class, how can you find the change in anything? What minus what? Final minus
Initial.
initial. So I can write that as P minus P naught. Final momentum minus initial position, momentum, right? Not position, momentum.
Right?
Now, I can also write that as mass times change in velocity. Okay, right? Same idea. And I can also write that as mass times v minus mass times v naught. I can write that as mass times v minus v naught.
Yes.
So what you're going to see as more and more, this unit of momentum and especially energy is going to begin to tie together a whole bunch of different things. So when you can set a whole bunch of things equal to each other, it's vital that you understand what you're keeping constant and what you're changing, Dylan.
If I didn't catch that egg, would force normal have killed it?
Absolutely.
Okay.
We'll talk about that later.
Yeah.
So, here's the story. If you want to minimize the force on the egg, you don't want it to break, okay? So, if you look at this, when I threw it, if you were to look at a momentum time graph, when I threw the egg to Dylan, did the egg initially have any momentum?
Well, I
No.
guess when you start moving your hands.
No. But now, I threw it to Dylan. So I took the egg from having no momentum to some momentum.
Correct.
C.
Okay? So I changed the momentum of the egg. So a lot of times you'll see change in momentum referred to as impulse. Okay? So impulse, that's a U, and change in momentum mean the same thing. So I imparted a certain impulse onto the egg. I took it from 0 up to some value. Okay? At this point, it left my hand. As it was flying through the air towards Dylan, do you think the momentum was changing?
Yes.
No, it was pretty much the same, right?
Right,
It
it
was
was.
basically a projectile over that short distance,
Yeah.
right?
Yeah.
Okay?
Wasn't accelerated.
So the momentum was pretty constant. Dylan caught the egg. What was the final momentum of the egg?
0.
0. So I took the egg from 0 up to some value. I changed the momentum. The momentum of the egg, that required a force. Momentum stayed constant. Dylan caught the egg here and slowed it down and brought the momentum back to 0. So our impulses were the same. I took the egg from 0 to something. Dylan took it from that value back to 0. The only thing different is the sign. I had like a positive change in momentum. Dylan had a negative change in momentum. Okay? Got the idea. So let's say that Dylan, instead of cradling the egg, Dylan just goes like this and just stops it right there. What's that going to do to the change in the momentum of the egg?
It's gonna happen quickly.
Yeah, it's gonna, that's
That
gonna
wasn't
be,
the question though. What's going to, I didn't say the rate of change in momentum. What's going to happen to the change in the momentum of the egg?
it's gonna go to 0 really
It's
fast.
the same amount.
So the change in momentum is the exact same. Okay? So if this is Dylan cradling the egg, okay? He's going to slow this down over a long period of time. If he doesn't cradle it, it becomes much steeper, right? So this is where this goes full circle. What does the slope of a momentum time graph give you? Force, because it's Newton seconds divided by seconds. Oh, the seconds cancel out. So when Dylan cradles it, and it's a shallow slope, what does that mean about the force?
Less force.
Less force.
No force hold.
If he just cradles it, it's still going to be the same change in momentum. But we talk about the rate of change in momentum. So the rate of change in momentum per unit of time on the cradle is a small number. So that creates a small force. If Dylan just goes like this, bam, catches it,
On force normal's gonna kill it.
well, some bad things are going to happen, right? Okay, so stop that camera. because we need to go spin around to the back. I need you to.